And you already saw the Kingdom Tower in Jeddah is over 1,000 meters high. And so it's already realized. And then we see that there are 12 in China, in the first 20 skyscrapers in construction in the world. And then there are about 17 in China in the first 20 skyscrapers in planning in the world. So according to the China Economic Weekly published magazine, it talks about the impulse of the ultra-height skyscrapers. Now, what are the paradigms of the skyscrapers? We think about all these factors, all the way from cost, saving, energy, safety, technology, fire, service, and operations, sustainability, and heat stress. And people think that this is not an energy-saving building because of its big size and tall and the height. But the theme for this forum is sustainable building. So how do we design better in the ultra-high building? And what can we do to make it work? So this is Dalian outdoor air design conditions. So in our research, we picked the summer and picked the spring season. And we picked the city Dalian as our model city, and we did some research. Now, this is the Dalian outdoor air design conditions. And this is the summer parameters. And the outdoor design temperature, the dry bulb temperature is about 20 Celsius. The winter, it's about minus 13 degrees is the outdoor design temperature for the winter air conditioning. Now, in terms of vertical distribution of the outside air, and through handset or TV, we can get the temperature change. We can get the humidity data. We can get the wind speed. But the vertical distribution data are not quite available. Maybe through a certain observation tower, we may be able to get some data above 1,000 meters. And this calls for special equipment. Our focus is on the low altitude and the high altitude. In the low altitude, it's what we set at 1,000 meters. If it's below the 1,000 meters, we consider that as a low altitude meteorological observation data. Now, this is a vertical distribution of the outside air. Now, you can look at this spot, real-time, the ground temperature and the humidity and some of the wind data. This is a software. It's called the BlueRF software. And this BlueRF model is built over a parent domain with 400 kilometers of spatial resolution covering all the Dalian area. This is a very good software. And you can do the calculation within this zone. You divide it into certain blocks, and you can monitor the ground level, the lake, the mountain, what kind of climate data, what kind of meteorological information. And these are some of the domains of the simulation. You can start from the ground level all the way to 1,000 meter height. Now, in January, we got this kind of hourly average temperature, and it changes over different height. And this happened to be on particular day and given particular hour. And different hour, you can calculate different temperature. It takes a lot of time to do this kind of calculation. So for every day, every hour, you can see the temperature change over different height, all the way from ground level to about 1,000 meter or 2,000 meter. Now, this is pretty much as predicted, about 0.5 Celsius change every 100 meter elevation. And through the model, through the calculation, it differs a little bit. Now, in the winter and the summer, you may have a different curve. In winter time, within the 1,000 feet, the temperature differs about 7 or 6 Celsius degree. Again, this is a rough estimate. And this is the current research we are doing. But basically, the black line is the average temperature change over different height. So it's a linear curve. Now, this is the hourly average temperature change with height in Dalian. And in April, in the top left, and this is the August, and the bottom is the October data. And in August, the temperature change from ground level to the 2,000 feet, but basically it's still a straight line. Now, this is the hourly average relative humidity change with the height on January in Dalian. Through calculation, we discovered something interesting. As you increase in height, the relative humidity, as long as it's less than 800 or 1,000 meter, the relative humidity continues to go up. But once you reach 1,000 meter or 800 meter, the relative humidity decreases. So the curve goes to the left. And we did not know that before. Again, this is the relative humidity. And if you look at the humidity, the humidity continues to go down as you go up, because the temperature decreases at a certain height, and so the relative humidity does change. Now, if it's a continental weather or it's a maritime climate, this is a significant factor to consider. Now, these are other months, like in August, the ground affect less. And once you reach 1,000 meter or the 1,200 meter, there will be some changes in terms of the relative humidity. In winter time, the relative humidity remains about 30% to 40%. Is a comfortable zone. Now, go back to the previous. The relative humidity remains at about 50%. So it's relatively dry at the ground level. As you go up, it's a comfortable zone. But in the summertime, it's a different story. So this is the temperature and the relative humidity change with height. So the relative humidity of the air increases with the increase of the height, but peaked at about 1,000 meter high over the peak point. The relative humidity of the air gradually reduced with the height increasing. At 1,000 meter above the ground, the outdoor air temperature is about 6 Celsius lower than the ground, while the relative humidity is about 20% than the ground. Due to the effects of the ground radiation and the sea breeze, air temperature and the humidity near the ground is relatively largely affected by the terrain and the different types of the ground radiation. The temperature changes significantly at the different time periods during a day. Now, this is the corrected value of the meteorological parameters at different heights in summer and winter. Now, you can have either the ground or 3,000 meter or 500 meter, 800 meter, 1,000 meter. You can do this for summertime and the winter time and calculate the dry bulb temperature, wet bulb temperature, and relative humidity. And also, you look at the the entropy does change, and the value of the entropy change at the ground level is about 76. But if you go up to the 1,000 meter, the value drops to 62.1. So it tells you that in the ground level and the outdoor temperature is already changed by the nature. The entropy is much smaller, therefore you don't have to use the manual air conditioning treatment to treat the air. And there's a wind speed factor. This is the vertical distribution of the outdoor wind speed, and there is a difference between the summer and the winter time. If you look at this according to different time of the day, in the evening the wind speed is faster. Averagely speaking, you can pretty much follow this curve. Another interesting thing that is in August, on the left-hand side, depends on different location, of course, but in August, the vertical distribution of the outdoor wind speed gradually increases along the height with a complex pattern. According to the calculated results, in August in Dalian, when the hourly average wind speed was about 5 meters per second, it is about 11 meters per second at a 500 meter high, and about 10 meters per second at 1,000 meter high. So it's quite an interesting change. So different height may have a different wind speed, and this at least is the data in August. So again, above 500 feet, wind speed reduces. So this gives us some important data for us to design the air conditioning system. Now we also did one for the January. This is the vertical distribution of the outdoor wind speed, and this is a little bit different from the summertime. In January, in Dalian, it's located in the northeast part of China, so wind speed is much higher. And the wind speed goes up as we go from ground level to 800 or 1,000 meter high. So the vertical distribution of the outdoor wind speed generally increases along the height with complex patterns. So this is a result of our testing and a model calculation. Now this is the effect of the wind speed on the heat transfer coefficient of the building envelope load. So the main effect of the wind speed on building energy consumption is reflected in the convective heat transfer coefficient of outer surface. However, due to the relatively small thermal resistance formed by the convective heat transfer coefficient of outer surface, the effect of the wind speed on the thermal resistance and the heat transfer coefficient of the building envelope is relatively small, at about 2 to 3%. And the effect of the wind speed on the building cooling load sometimes even can be negligible. Now, we worry about PM 2.5 and PM 10, that is the air pollution index. Now, we don't know how to do this research better, but this is what we got so far. And this is in Tianjin at different time of the day. And if you're going to PM 2.5, it's at 100 meter, you will see a worse pollution. After 100 meter, the PM 2.5 level goes down. This is in Beijing. They measure all the way to 3,000 meters. And there are certain conditions you have to meet. The first one on the left-hand side, as the wind speed is high and the PM concentrating in the lower ground is pretty much the same as the PM 2.5 level in the higher altitude. So when you have the strong wind, then the PM 2.5 concentration pretty much the same, whether it's the ground level or the high level. Now, on the third one, if the low wind speed occurs, then if it's below 500 meters, the PM 2.5 is relatively high, but above 500 meters, the PM 2.5 concentration reduces at this particular zone. So in other words, when the wind speed is slow, then the PM 2.5 cannot be dispersed, so it stays under the ground level. And at 1,000 meters or 1,200 meters, the PM 2.5 concentration drops significantly. It's probably dropped down by 90%. So if the PM concentration in the low wind speed, then the PM 2.5 at the higher level is relatively low. Now, given what we just reviewed, the summer temperature changes accordingly. The relative humidity in the wintertime and the summertime differs, offer different comfort level. And likewise, with the pollutants, it does matter which what the height is. And some location in the summertime at 1,000 meters, it becomes a very nice zone. And at that height, you can enjoy the good weather and good pollution-free. So, in fact, if you go to the higher altitude, and it's a pretty good and comfortable zone. Now, let's talk a little bit about the air conditioning load. Again, this is the software we have. This is the air conditioning load calculation. And the calculation parameters are as follows. The heat transfer coefficient for the exterior wall is about 0.6 watts per m squared multiplied by K. The heat transfer coefficient of a glass curtain wall is about 2.8 W per square meter dot K. And the shading coefficient is 0.5, and the window wall ratio is about 0.7, and the indoor design temperature in the summer is 26 Celsius, the relative humidity is 60. And now let's look at the office cooling load in summer. And depends on where the location is. This one is supposed to be westward. This is an arrow here, and the bottom left is south, and the bottom right is north. Again, the load will go down as you go up. And this one is for the apartment cooling load in the summer. This is the hourly cooling load per unit area at the different height in summer. Now, as shown in the figures, the change of the outside air conditioning due to the height changes can significantly affect the cooling load of skyscraper. Now, this is apartment heating load in winter. Now, this shows the room heating load index at various heights. And the heating load increases when the height increases. The maximum heating load occurs at the height of 1,000 meters above the ground. Now, this is a percentage of the cooling heating load on the ground level. And the one on the left is the percentage of the cooling load on the ground level. The top right is the percentage of the heating load on the ground level room. Now I want to talk a little bit about the ultra-low energy consumption in the skyscraper high floor. Now, the function of at high floor in skyscraper. Now, for a typical super high-rise building, the high floor areas are mostly residential apartments and hotels. And this paper takes the apartment as an example to study the air conditioning load characteristics in high floor areas of the building. This is the analysis of the ultra-low energy consumption. Based on the load characteristics of a high floor area of skyscraper, improving the building envelope, utilizing the variable shade system, optimizing the outside air intake, and installing high-efficient energy systems can achieve ultra-low energy consumption, low carbon, and even zero carbon emission. Now, this is the optimization of the building envelope. And the heat transfer coefficient of the external wall is about 0.3. In the European countries, they can do at the 0.2 watts. Now, heat transfer coefficient of the double breathing glass curtain wall is about 0.8 watts. And by utilizing variable shading, the shading coefficient in the summer is 0.2 and 1 in winter. This is the hourly cooling load per unit area at different height in summer. So the room cooling load index at 1,000 meters high are 33.3 on the east side, and so on and so forth. And the cooling load index decreases by almost 50% in the east side. Now, this is the energy saving optimization of outside air intakes. The outside air temperature in Dalian area decreases when increasing the height from the ground, so is the outside air enthalpy in summer. At the height of the 1,000 meters, the enthalpy of the outdoor air is about 14 kilojoules per kg, less than that of the ground level. Now, this is the hourly cooling load per unit area at the different height in winter. Actually, heat recovery can reach about 70%. This is the actually the heating load. So when the heat recovery efficiency is 70%, the room heating load indexes at the height of 1,000 meters are about 12 watts per square meter in the east and west, and then 10.8 watts per square meter in the south. Now, this is the analysis of the ultra-low energy consumption. By improving the insulation of building envelope, utilizing various shading system, and installing heat recovery, and you can do a lot. Now, this is the analysis of ultra-low energy consumption. So, it is highly possible to achieve ultra-low energy or even net zero consumption in skyscraper by combining the above energy efficiency measures with even more advanced technologies such as solar curtain wall power generation and wind power and other renewable energy resources. This is the relationship between the number of floors and the building energy consumption. Now, these are some of the data from the last forum. As the number of floors go up, the kilowatts per hour per square meter will be reduced. So let me come to the conclusion. Now, the vertical variation of the outside air conditions on skyscraper have a significant impact on the HVAC loads at different height. Now, the cooling load of skyscraper reduces significantly along with the height increases, and the skyscraper in the tropical and subtropical areas are easier to achieve low energy consumption. And based on the load characteristics of the high floor area of the skyscraper, improving the building envelope, utilizing the variable shading system, optimizing outside air intake, and installing high energy efficiency system can achieve the ultra low energy consumption, low carbon, and even low zero carbon emission.